Okay, so hi, Assalamualaikum. My name is Nazimin Azila. So I will talk about introduction. The introduction is the precise speed management of rotating machinery is a key difficulty in the field of industrial automation and contemporary control systems, having broad applications in numerous technical fields because of their superior speed torque characteristics, simple speed control mechanism, and dependable performance under a variety of operating situations. Direct current DC motors are essential actuators in a wide range of industrial applications. The principal actuator in the system under study is a DC motor and the mechanical load is a blade. Under various operating conditions, the control goal is to maintain precise rotational speeds of 900 rpm and 1500 rpm while guaranteeing low overshoot, quick setting times, and 0% steady state error. Okay, so for manual PID tuning, it's a technique that changes the gains of a controller by monitoring system behavior like rise time and overshoot through techniques such as trial and error or Ziegler-Nichols. This method assists engineers in gaining a greater insight about the system, and this method is time consuming and is highly reliant on the experience of the operator. Okay, so for automatic PID tuning, automatic tuning is a software-based method like MATLAB or Simulink algorithms that is used to compute optimal controller gains, satisfying specified performance requirements such as low overshoot and short settling time. This approach tends to give more steady and strong performance, particularly in the complex systems, and so it is very appropriate in the contemporary control. Okay, so for problem elaboration, variations in load, electrical supply, and system parameters can cause significant speed deviations, leading to steady state errors, poor dynamic response, and potential instability in an open loop setup. These issues reduce efficiency, increase mechanical stress, and compromise operational safety. To address this challenge, a closed-loop control strategy using a PID controller is implemented. The controller continuously monitors the actual blade speed, compares it to the reference value, and automatically adjusts the motor input to minimize error. Through system modeling and MATLAB simulation, the PID controller is tuned to enhance performance, reducing steady state inaccuracy, limiting overshoot, and improving the system's ability to handle disturbance. This approach ensures reliable and consistent speed regulation under changing operating conditions.
So for our simulation setup in Simulink, first one, figure 2.4.2 shows our open loop setup. This allows us to observe the motor's natural response to a step input without any corrective feedback, establishing our baseline performance. Move on to manual PID tuning on the top right. Figure 2.4.3 introduces a feedback loop with a manually tuned PID controller. Here we adjusted the proportional, integral, and derivative gains ourselves to meet specific design requirement. So the third one is comparative analysis on the bottom left, figure 2.4.4. We run a parallel simulation comparing PI, and PID controllers. This setup allows us to see exactly how adding integral and derivative term improves stability and reduces steady state errors side by side. And the last one is automatic PID tuning. Figure 2.4.5 shows our automatically tuned setup. We use the Simulink PID tuner to optimize our gain, providing a benchmark to compare against our manual result. That's
Hello, my name is Izwanul Irzan. So, for my part, I will explain on the mathematical modeling and manual pit controller design. So, first, the electrical and mechanical parameters of the DC motor and blade load were identified. Then, the armature circuit equation and mechanical torque equation were formulated and converted into the Laplace domain. The electrical and mechanical parts were linked through the electromechanical equation, and the equivalent inertia was calculated to account for the blade load. Finally, all the parameters were substituted to obtain the overall transfer function, which is used in the next step for stability analysis and manual PID tuning. Okay, so next, after deriving the transfer function, the Ziegler-Nichols tuning method was applied to determine the controller gains. The first step was to identify the stability limit of the system using the Routh-Hurwitz stability criterion. From the Routh table, the range of stable gain was obtained and the critical gain denoted as KCR was determined. At this value, the system operates at the boundary of stability and exhibits sustained oscillation. Using the critical gain, the oscillation the oscillation frequency was identified and the period of oscillation was calculated. These two parameters are essential for applying the Ziegler-Nichols tuning method. Finally, the PID controller parameters were calculated using the standard Ziegler-Nichols formula, as summarized in the table. These values provide the initial PID gains used for controller implementation and performance evaluation.
Assalamualaikum and greetings to Dr. Diman. My name is Muhammad Sahih. My message number is 63050. So today I'm going to explain about the result because I made the estimation. So we already made three settings. That is for open loop, comparison for PPI and PID, and lastly for the manually and auto-tune PID controllers. So for the open loop system, we got the result as without feedback control achieve only 53% of the target speed, that is 50 radian per second versus 94.25 radian per second. So it demonstrate the significant statistic error and confirming that the necessity of the closed loop control. Then for the control comparison, we have PPI and PID. So the P controller provide fast response but maintains 5% steady state error. For the PI controller, eliminates steady state error with moderate 5% overshoot. And for PID controller, delivers optimal performance with minimal overshoot and faster settling time for approximately 0.3 seconds. So we continue to the next slide. For the third setting is I do the manual versus automatic tuning. So where the manual tuning use Ziegler-Nichols method as its aggressive behavior with 60% overshoot and peak is 155 radian per second and the oscillatory response. For the automatic tuning demonstrates superior performance with conservative, stable control and overshoot below 10%, meeting the design requirement. And for the performance summary, all the closed loop controllers successfully achieve the target speed. The PID controller with automated tuning provides the best balance of fast response, TR equals to 0.02 seconds, and minimal overshoot under than 10%. Quick settling time 0.2%, and zero steady state error, satisfying all the design specification for 900 RPM bit control application, and also 1500 RPM bit speed control application also. So that's all for my part. Thank you.
Okay, hi, my name is Muhammad Lakuna Kim Ramli. We'll talk the last for our presentation is conclusion. A PID control system for precisely controlling the speed of DC motor driven blade has been successfully constructed and validated in this work. It proved that it could consistently reach and sustain goal speeds of 900 rpm and 1500 rpm while adhering to stringent performance requirements through the theoretical analysis and simulation. The outcome validated PID control as a very successful technique that can convert simple electromechanical system into a precise industrial grade mechanism. From mathematical modeling to performance evaluation, the methodical procedure produce a useful engineer insight and workable control solution. Emphasizing the significance of appropriate controller tuning and practical implementation issue.